So in section 3.4, we're going to look at addition and subtraction algorithms. Algorithm just means ways of doing things, okay, or processes. And then we're going to also talk about mental estimation. So to start with, we're going to do addition. And I'm going to show you some things that maybe you've seen before in terms of models for doing addition, and some that maybe are brand new. The concrete model is one I'm sure you've seen before, but it might have been a while. So in the concrete model, we would actually use either physical blocks or images of blocks to add things together. And you've been working, or you've seen me use or bring those base 10 blocks, those red blocks, remember, before? This is the idea here. So when you have 34, you would have 3 longs, and then 4 units. And a unit is the little bitty blocks. Okay, so that's number 34, you know, more or less. And then we have 18. So with 18, I have 1 long, and then I have 8 units, like this. And if you're working with kids, what you can physically show is that if you start with the little units, how many little units do I have here? There are 12. And I could take 12 of them and I could do like I would do with Legos, right? And I could stack them all up into a stack of 10. And once I stack them up into a stack of 10, that's a long. So I have the ability sort of to trade up. So I'm going to actually shift this around a little bit to move these closer together. So there's all my longs sort of grouped together now. Here's all my individual units grouped together. And if I were to take 3, 6, 9, 10 of them, the ones I've highlighted, and I were to trade them in, right? It's like trading in 10 pennies for a dime. A dime. My goodness. I said 3 even. 10. 10 pennies for a dime, right? So I'm going to take 10 units and I'm going to change those in so that I end up having a long. So I have the original 4 longs. And now I have 1 more long. And how many units am I going to have left over? 2. So I can physically see when I'm done that I have 52. To set them apart or to distinguish them, you might want to put sort of some kind of a distinguishing mark around them, like circles or something, and the 2 circles are equal. But any questions on that? It's the concrete model. It's concrete, touchy-feely, right? Tactile learning, I can piece these together, I can trade things up, I can see how this whole carrying principle actually works. The next model is our standard algorithm. All right, so the standard algorithm, super efficient. Efficient means quick to do. But there's kind of some hidden pieces to it, like a why does it work going on, that are often unclear to kids. And if they aren't good at remembering the exact details of the process, they can't replicate it because they don't really understand what the process was doing. So this process works by adding the units together, right? The 4 plus 8. And when you add 4 plus 8, you get 12. And you write down a 2, and what do you do with the 1? You carry it over. Now, does anybody know why you do that? But why? Okay, because when I do 12, I have a 10 and 2 1s, right? So the 2 1s stay in the ones place column, and the 10 moves into the tens column. That's what's really happening there. All right, cool. And then we have 1 plus 3 plus 1 to give me 5 in the tens column. Okay, super efficient, and you guys seem to have a real good understanding of the why. But let me tell you what, I have seen kids do this before. Ah, my screen's moving around on me. Oh my word. How could they get 512? They just wrote a 12 in the ones column. Can you see how that would happen? Or why that might happen? Yeah. So we have to be a little bit more careful with how we explain sort of the shortcuts of what we do. There's another version that kind of blends together that concrete model and the standard algorithm, and it's called the expanded algorithm, and it looks something like this. It takes the number 30 and it breaks 34 and it breaks it apart into 30 and 4, and it takes the number 18 and it breaks it apart into 10 and 8. Okay? And what it does is it lines those up. I have 30 plus 4 plus 10 plus 8. And I can add from left to right or right to left here, doesn't really matter. I get 40 here, and I get 12 here when I do that. I'll show another version of this too. But then the 12 is a 2-digit number that's got 2 individual digits, so I can break it apart again. I have 40 plus 10 plus 2. And then I've got 40 and 10 to give me 50. You wouldn't necessarily write down all these steps, I just want you to see where they're coming from. That would be 52. That's really what you do when you do that concrete model and you're moving all those blocks around. That's what you're doing, is you're regrouping things together. By the way, so I know when I learned this, it was called carrying, like what we did over here was called carrying. You don't hear that used very much anymore. You hear the phrase regrouping used, which is really quite better because it's a very descriptive what it's actually doing. Not what it looks like, because carrying is what it looks like, but regrouping is what you're mathematically doing. Does that make sense? So I think it's a good move on language. Let me show you one other version of the expanded algorithm, just so, and I think this other one is the one that your book actually shows, so that way if you look back at it, you're like, oh, she didn't show me that. You won't do that, okay? So it actually breaks it down as to saying that this is 3 times 10 plus, what did I have, 4? 4 times 1, and 1 times 10, and 8 times 1. So it looks like this. Instead of 4 times 10 instead of 40, I have 12 times 1 instead of just 12. And then I break it down. So I have 4 times 10 plus 1 times 10 plus 2 times 1. And then I can combine those to be 5 times 10, 2 times 1, 52. Now, even if your kids didn't use this all the time, it can be very helpful for understanding. If you can see it happen in an expanded view, one of these or the other one, a few times, the standard algorithm starts to make more sense. We start to understand why we're regrouping the 1 into the tens column, that sort of thing. Same thing with concrete model. You don't want kids drawing pictures on every single problem. They don't have time to do that in general in a standardized test or something like that. But if they can get the concrete knowledge from that model, then they're able to use the standard algorithm and confidently know what they're doing and why it's working. Does that make sense? Okay. Left to right algorithm. So this one's fun. Math is kind of weird. Math is not like reading. When we read from left to right. And when we add from right to left. So that's not super helpful for children who are learning both things at the same time. Can you see how that could be a problem? I can. I can see how that would be very difficult for kids who are learning both of those things and maybe even struggling with one or the other of them to understand why one is one direction and the other is the other direction. So the left to right algorithm is one where it doesn't matter which direction, where it allows you to start from the left-hand side instead of from the right-hand side. So let me show you with this one. I've got 1534. Plus 32, 18. So we start with the right-hand or the left-hand column, and I've got 1 plus 3. But of course, 1 plus 3 in this column means 1,000 plus 3,000. I'm writing this out for your benefit to the side, not because a child would write it out. Okay? So when I'm really adding the 1 and the 3, I'm adding 1,000 and 3,000, and I'm going to write down 4,000. That's what the child would write down. So this is sort of like teacher notes on the side because you're the teacher, and what the student is doing is on the left. Now let's move to the next column, the hundreds column. 5 and 2. So 5 and 2 is going to give me 7 in the hundreds column, so that's 700, right? Because I really have 500 plus 200. And then I've got the tens column. I have 3 and 1, but it's really 30 and 10, right? Which is 40. And then the final column that I have here is 4 plus 8. And 4 plus 8 is the first one I have that give me a double digit, actually. It's the number 12. But I just write the number 12 down the way it shows. So I have a lot of zeros here. I can keep even adding from left to right at this point, and most of them actually give me a single digit in their columns. This is 4, this is 7, here's 4 plus 1 is 5, and then I have 2. So 45, 72 from left to right. It's not terribly efficient. I get that, but sometimes efficiency is not the goal, all right? So it's very nice for those who are working with that whole idea of addition versus, left to right versus right to left for addition versus reading. Yes, Brooke?
So let's say like the 3 and the 1 equals 9.
Yeah.
And then you would have 9 plus 1 equals 10. What would you do with the extra 1? Would you just add it over?
Yes.
Okay.
Well, or you could do the same thing you did again, where you're breaking it down again one more time. Yeah. So in some problem, well, and also, you know, when kids are working with this algorithm, they're far less likely to be working on 4-digit addition, right? They're probably working with double-digit addition, and you're not going to have those kinds of things happening very frequently because the numbers are just not as long. So that's another thing too. All right, the lattice algorithm. This one's super fun. So I would like for you to draw a rectangle. Your rectangle needs to be split into 4 boxes. So cut it in half. Whoops, I don't know why it's dotted. Hang on, let me fix that. Cut it in half, and then cut it in halves again. They don't have to be perfect, okay? The reason you've got 4 boxes is because these are 4-digit numbers. If I had 3-digit numbers, I'd have 3 boxes. Everybody go with that? Okay. I think I have enough space the way mine's drawn. We're going to add these numbers, or we're going to write these numbers down above the boxes. So 1894, 3218. And I'm going to take each of my boxes and I'm going to split them in half diagonally. And this is why it's called a lattice, is because it looks like a lattice. This one's nice, again, because you can move from left to right or right to left. Doesn't make any difference. Won't hurt anything either way. So just because we can, let's go from left to right. So when I add 3 plus 1 together, I get 4. And if I get a single digit number, it goes in the bottom box. If I get a double digit number, then it goes in the top and the bottom box separate, right? Just like the number. So if the number had been, like 11, it would have gone, or let me do 12. I'd put a 1, 2. That would be 12, okay? Our number's just 4, so we're going to put a 4 here. 8 plus 2 would be 10, so I'm going to put a 1 here and a 0 here. 9 and 1 also happens to be 10. 4 and 8 is 12. We keep adding that one together. Okay, and then what you do is that you add along diagonals. So here you do need to go back to the right-hand side. You have to start in the bottom right-hand corner. This is the number 2. In my second diagonal here, I have 1 plus 0, so that one would be 1. In my middle diagonal, I have another 1 plus 0 for 1. And in my far diagonal, I have 1 plus 4, which is 5. Now, let's say, for instance, you did add up something that was too big. Like, let's say I added one of my diagonals together and I got 14. It's okay. I would write down, let me say it's right here. I would write down the 4 here and I'd carry the 1 to the next diagonal. So I can still do that. So you might be looking at this and saying, well, but what benefit? How is it better? I mean, there's more writing involved. It's not as efficient. It doesn't have the intuitive sort of flavor of it that the other one did. It does have a nice grid structure. Structured kids, the ones who need that structured form, this is a very appealing form for them. It also limits the addition to being smaller for the most part. All right, I don't have to add as big a numbers and carry as much when I'm going through this process. All right, scratch algorithm. On this, I would like for you to write that it's used when you add lots of numbers together. And I don't mean big numbers, I mean multiple numbers. So you notice my example has 4 numbers we're adding, right? So this is like for a list of things you're wanting to add together. It's really impractical otherwise. I think your book uses a couple examples where it doesn't have a list, and it kind of falls short of what's the point. All right, but for lists of numbers, it's super cool. I actually, once I learned this one, this is how I add lists of numbers together now. It actually works so well. So what you're going to do is you're going to write them, vertically, just like we've been writing all the other problems. 34, 18, 69, 87. Okay, we're going to start in the top, and we're going to add our way down. Here's what happens. Anytime we get to 10 when we're adding, we're going to scratch the number, and we're going to stop thinking about that 1 that we just scratched. Let me show you. 4 plus 8 is 12. 12 is more than 10, so I'm going to scratch, and instead of continuing to remember the number 12, I'm only going to remember the number 2. So I ignore the 2-digit number, and I only remember the 2 in the number 12. And I keep going. Now I have 2 plus 9, which is 11, which is 10 or more. So I scratch again. And what's the 1's digit in 11? 1. So I only remember the 1. And then I add 1 plus 7 together, and I get 8. How many scratches did we make? 2. What that really did is every time I scratched, I sort of ignored the 10, right? I ignored the tens column. So I ignored the tens column twice, which means I ignored 2 tens, which is a total of 20. So I need a 2 in the tens column now for the 2 scratches, because I ignored 2 tens. Now I got to compensate for those ignoring. We're going to do the same thing in the next column. 2 plus 3 is plus 1 is, plus 6 is 12, and that's my place where I would scratch. 12, ignore the tens digit, I remember a 2. 2 plus 8 is 10, so I would scratch. What's the 1's digit in the number 10? It's a 0, yeah. And then in that tens column, how many scratches did I make? I made 2 of them, so I would carry the 2 over. I don't actually have anything in the hundreds column, so this would just be 2 in the hundreds column alone. So why does it matter? Well, think with me about what you would do on the ones column otherwise, okay? If you were just adding with standard algorithm. You do 4 plus 8 is 12, and then you have to add 12 plus 9, which is probably not in your list of simple addition facts that you learned. And even if it is, now you get to 21 plus 7, and that's definitely not in your list of simple addition facts that you learned when you had your flashcards. Do you see what I'm saying? Scratch addition allows you to only have to remember the single-digit additions that you would have learned as the first steps in learning addition. And that's its benefit. So I actually have smaller numbers I'm adding along the way. 208. Yes, ma'am.
Spending time in a second grade classroom right now.
Yeah.
And they are learning how to add double and triple together, two numbers together.
Okay.
And they're doing kind of like a T chart. Is that a strategy to go along with the standard algorithm to line the numbers up correctly?
They're probably doing it kind of like they're doing Lattice, yeah, where they're giving themselves a grid. Is that what you mean?
Yeah.
Yeah, it sounds like it. Yeah, it sounds like it.
They'll have a lot of problems with lining the numbers up incorrectly, especially when they have a 3-digit number and a double digit. They'll line them up incorrectly, and so they use a T chart, is what she calls it. The teacher calls
Sure.
it. And
Yeah.
I don't know if that with the standard
I don't know that it's, I mean, it may have a name within the curriculum that she's using, and it may be T-chart from what she's saying, but what they're doing is they're just giving structure to the location, which is a lot of what like the lattice algorithm does, is give that kind of a structure to it too. But it sounds like that's what they're using it for, is more than anything just an organization tool, which is good. And then they're probably using the standard algorithm within that, aren't they? Yeah, it sounded like it. Yeah, that's cool. Great. And of course, I mean, this list is certainly not going to be exhaustive, right? There's actually another algorithm that I don't teach in this now that's been in one book that I've had before too. So, you know, and these things change. By the time you guys are out teaching for 10 years, there's probably going to be a bunch of different other strategies that people are using and finding work really well for kids with certain, you know, challenges or disabilities or different things too, and you're going to have this bigger repertoire of ideas. All right, let's take a look at a couple of subtraction algorithms next, or a few subtraction algorithms. Some of them are going to look very much like the addition algorithms. That is, their names are the same and they work very similar. The first one is an example. It's concrete model for the number 34 minus 18. So we're going to draw 34, which would be 3 longs and 4 units. They're definitely not the most uniform units that I've ever drawn, but we'll be okay with them. There's 34. Now, if a kid really had these objects in front of them, you would ask them then to take 18 of them away. Well, taking 1 long and 8 units is what that would translate into, right? Easy to take 1 long away. Not so straightforward to take 8 units away, because I don't have 8 units. I only have 4 units. So what do I have to do? Well, I need to take one of my longs and do what with it? I need to break it down, right? I need to take one of my longs, and I need to break it down into 10 units. So what I need is I need to rewrite this expression, whoops, I'm going to draw this, as the 2 longs instead of 3. Sorry, I didn't mean to draw it lower. And then I have, whoops, the same 4 that I had before, and then now I also have 10 units that have been, you know, sort of decomposed from the long. Okay. Now, this is the same value that it was before, agreed? I didn't change any value. I just changed how it looked. So it'd be like having 3 10s and 4 1s in your wallet, and you would change one of the 10s into 1s. Now you have 2 10s and you have a whole bunch of 1s in your wallet instead. Same money, right? But it adds up different, and add up differently. It adds up the same, but it's structured differently. But it allows you to actually take away, remove, subtract 1 long. So one of these longs, I'll highlight it, is going to be removed. And I can actually remove 8 of my units. So everything I highlighted is going to be removed, which would leave me with 1 long, whoops, 2 long, or 1 long, yeah, I said that right. And how many units am I left with? Somebody said it, 6. So my answer is 16. Now in the standard algorithm, any questions on the algorithm before I move? Okay. In the standard algorithm, what do we do when we subtract? How did you learn to subtract these? Took a 3 and it became a 2, and the 4 became a 14, yeah? And we called that process borrowing. And we are, I mean, like we are, it looks like we're borrowing, that sort of is the visual imagery going on. What we're really doing is regrouping. We took a 10 and we turned it into 10 ones. So now I put a 10 in the ones column with the 4 that were already there. Then I can do 14 minus 8. That's the same thing I did visually on the screen before to give me 6. And 2 minus 1 would be my 1 for 16. Okay, so I'm regrouping my values. And if I use my expanded algorithm, I can see that a little bit better. I have to do more writing, but I can see it a little bit better. So again, I would have something like 30 plus 4. And I have minus 18, so it's minus 10 and minus 8, because that's minus 18, right? So I'm perfectly capable of doing 30 minus 10, but the 4 minus 8 doesn't work very well if you don't know anything about negative numbers yet, right? Not so good. So we actually have to regroup. So the 30, 3 tens, will become a 20, and the 10 that I just took away will be added to the 4 that's over here. That's the same 34, it's just grouped differently. But it's grouped in such a way I can subtract. 20 minus 10 would be 10, 14 minus 8 would be 6. This is 10 plus 6, which is 16. Okay, there's one more subtraction algorithm. Yes, ma'am, sorry.
How would you explain why you subtract 10 and 8? Like, it makes sense, but you add the 34, like it's written 30 plus 4, but it's written 10 minus.
You could do it like this. You could talk about the fact that you're doing 10 plus 8 like this, and then a negative is a part of both pieces. It's a minus a 10 and minus an 8 because we're subtracting all of it. You could probably also talk about the fact that we're taking away 18, so we have to take away 10 and take away 8 both. You could use that kind of language. Yeah, it's a good question. Okay, this is my favorite subtraction algorithm because I think it's kind of clever. I think it's interesting. So the whole goal, please write this down in big, bold, highlight it, whatever it takes here, is that you have no borrowing. And I mean none, ever. You will not borrow, you will not regroup, there is none of that going on. So there must be something else going on because we know that sometimes you kind of need to do that, right? So let me show you how it works. You're going to write it out just like we have been, 834 minus 158. And you're going to recognize in the far right-hand column that you need to regroup or you need to borrow. 4 minus 8 doesn't work. So what do you do instead? Well, what you do is that you need this 8 that's on the bottom. You really want it to be a 0 because zeros are really nice. So what would I have to add to 8 to get it to become a 0? A 2. Now when I do that, it becomes 160, right? But I can't just go adding 2 there. I would also have to add 2 to the top number. So what is 834 plus 2? 836. Whoops. So looking in just the ones column only, would you have to borrow? Nope. 6 minus 0. Easy peasy, right? But what do you notice in the tens column? I got the same problem I had before, right? So I'm going to do the same thing again. I need to add something to the 6 to turn it into a 0. We're always turning things into zeros. This is not randomly guess and check kind of adding and seeing if it works. We're always turning things into zeros. What would I have to add to the 6 to make it become a 0? A 4. So it's in the tens column, so I'm going to add a 40. So what is 160 plus 40? 200. How about 836 plus 40? 876. Can I now actually subtract the whole thing without borrowing? Yes. What is 876 minus 200? 676. All right, there's basically 2 other sections of material that are coming next. One is called Other Bases. And Now, you guys thought from section 1 that we were done with other bases. You were wrong. We're going to do a little bit more with it. And then the next section is called mental math, okay? And we are going to do those 2 sections next time. This is a really good stop spot, so we're going to stop here today.